Good morning, everybody, and welcome to the session of the Quantum Technology Training for Policymakers. I'm Oxana Mishina. I'm a researcher at the Italian National Institute of Optics at the CNR, and I will be moderating this session for you. And I would like to thank a lot all the coordination and support action of the Quantum Flagship QCATS project for preparing this training. Today, we are going to talk about sensing, quantum sensing, and the most impressive part of it that is actually covering sensing on very different scales. So the topic of today's session is quantum sensing from the human eye to the planet Earth. And these are exactly the scales we are going to cover in this session. I will right away start by inviting our first speaker, who will be presenting Patrick Montague. Please, Patrick, come on stage with us. Patrick is the R&D Manager at the NKT Photonics in Denmark. And he will be presenting us a Sequoia project that is creating a new device for retinal imaging, for sensing our human eye. Patrick is the head of Future Technology Department at NKT Photonics, where he's responsible for scoping and assessing the feasibility of new laser systems, as well as expanding engagement in emerging markets to grow the NKT Photonics product portfolio. He has been with NKT Photonics since 2017 and working in several years in engineering roles developing novel laser systems. He studied at the University of Auckland, where he gained a PhD in physics and the undergraduate degree in optoelectronics. In relation to the quantum technologies, NKT Photonics has been instrumental in supplying single-frequency lasers for trapped atom physics, squeezed light, and also photonic quantum computing, and as you will see today as well for sensing. Patrick's department played a leading role in development early prototypes of these lasers and identifying new development opportunities. So we are very much looking forward to hear your presentation, Patrick, about how Sequoia will impact our future of eye diagnostic.
Okay. Thank you, Oksana. So, yeah, I have some slides for you about the Sequoia project. This is a project on quantum optical coherence tomography. And let me get right into it. So the most fundamental thing to understand about optical quantum OCT is to first understand classical OCT. And classical OCT is something that uses low coherence interferometry in a Michelson interferometer. It's what's shown on the left here, using a light source of some kind with low coherence, with a high number of photons in comparison to a quantum OCT system. And so better thought about as a wave interferometry. And there, the light goes through these two paths. One of the light paths goes to the sample, say the eye, and the other is a reference arm which moves back and forth in time domain OCT. And then when the reference arm length matches the length of some scattering layer of the object that we're looking at, then we will get a strong reflection, a strong interference rather, and we'll be able to see the layers of the eye, and that's what you see in this GIF in the left-hand corner. And in this way you can see deeper into the eye, a cross-sectional depth image into the eye, and that's really important for instance, macular degenerative disease detection, because the primary way that this shows up is by the thinning of the retinal layers, and they only thin by tens of or hundreds of nanometers per year, and being able to catch them early as they degenerate and stop them with treatment is critical. And so that's where quantum OCT comes in. The motivation for this is that we're trying to get a higher resolution. In theory, we should be able to double the resolution or half, have 2 times better resolution by this quantum effect. And in theory, that would be enable you to detect this macular degeneration twice as quickly. So they're very similar looking imaging setups, the two. There's a few differences that are important. First, we're using just 2 photons in the interferometer path. So we generate that through spontaneous parametric down conversion in a crystal, and then the 2 photons that are emitted go off in 2 different directions down the interferometer path. It's called a Hongu-Mandel interferometer rather than a Michelson, but it looks quite similar. And of course, then one goes to the object arm, the other goes to the reference arm, and then they meet at a pair of single photon avalanche detectors. And what we're measuring here, instead of the interference in the wave case, we're measuring a coincidence drop. When 2 photons, when the path lengths are matched, like in the previous, then the 2 photons arrive at the same time and are pushed down together to one detector rather than having 2 separate clicks, and that means we no longer have a coincidence, so we have this coincidence drop. And that's the spike that you see, the dip that you see at the bottom right corner. So the Sequoia project has quite a number of partners. On the hardware side, NKT Photonics, which I represent, is making the light source. We're looking at orbital angular momentum on the photons, which the hardware is coming from TU Delft. DTU, the Danish Technical University, is developing the interferometer itself and taking the measurements. It's building the test bed in their lab. And then MPD in Italy is developing new SPAD detectors. Aside from the hardware, then we also have several other partners involved in understanding the quantum theory and doing generating some samples for us to use, which I'll talk about a little later, developing OCT software and looking at this AI, so looking at the machine learning for segmentation of the retinal layers in the images we take, but also looking at algorithmic control of the orbital angular momentum that we put upon the photons. So quantum OCT is a fairly new topic. There's been a couple of groups, several groups that have looked at it over many years, but no one has put I wouldn't say there's been a significant amount of research in the field. It's a fairly challenging measurement modality to do, and so NCU in Poland has been an important partner for us in terms of understanding how quantum OCT works overall. But also their task in the project has been, when we look at this SPDC, the single photon generation, spontaneous parametric down conversion, how is the orbital angular momentum affected by this? And I don't want to go into too much detail, but you can see here that we draw the OAM control here and here. We might also like to place that orbital angular momentum control here outside before the photon is generated, because it's a lossy process, and one of the things that's really highlighted here is the importance of having low loss throughout the system. And some of that loss is very unavoidable. Samples have low reflectivity in general. And so that's a key thing for NCU to work on and understand, to model the noise sources and to look at the beam propagation through the scattering sample medium. The topic that NKT has been working on is, I mentioned, the light source development. That is a pulsed laser in a all normal dispersion fiber, so generating supercontinuum, which is a primary competence for NKT. But this is a new kind of supercontinuum. Specifically, it's a coherent supercontinuum source, which means it has a very low relative intensity noise. And it's akin to what is typically described in the market and in literature as a frequency cone. So it has very distinct lines, longitudinal lines, which can be picked out. And the light source that we're trying to generate is feasibly between 500 and 800 nanometers. But our goal here is to frequency double the light to a shorter wavelength and generate a UV supercontinuum. And that would be something that's very new. The purpose that we're doing that is both for the general benefit of having a product like this. This will be very valuable to NKT, but for the project specifically, we'd like to generate entangled photons at wavelengths around 500 to 800 nanometers, which means you need to have a light source with half that wavelength to generate it. And we've worked on this in combination with, in collaboration with PTB, who have been able to measure the light source at its extremely low relative intensity noise of 0.055%. NPD is working on the single photon detectors. So in the image that I showed earlier, there was two SPADs. In this case, NPD has made an array, SPAD array, which means that single detections can occur on different pixels of the array, and these can be used to make the coincidence measurement, which is a useful way to cut down on having two different components as merged into one. So the focus for their design was on having low noise, low dot counts, and single photon detection is obviously critical to work within the range that we are using, so it's 500 to 800, to increase the number of pixels they had previously had up thousands, and to optimize this readout around our parameters for coincidence detection. The orbital angular momentum that was done at TU Delft that they're underway with. So this is a project where you use a spectral light modulator and apply a phase to the light so that it picks up this new phase relationship across the spatial profile of the beam that we call an orbital angular momentum. And this gives us greater degrees of freedom in terms of quantum information. So this could be used to improve the edge definition, and in theory, it could also be used to discriminate chiral surfaces. At the moment, we're looking at how the OAM propagates in scattering media and through the SPDC process. And the University of Valencia is involved in this, as I mentioned earlier, in terms of training the algorithms to optimize and control this OAM through the scattering media. DTU are working on building this breadboard, integrating the OAM, and they have a history working on OCT already and are kind of stepping into quantum with this project. So they're very skilled in making OCT setups and working with OCT imaging. It's in fact Norbliss, a spin-out from DTU, who is working on the OCT software and is a company developing OCT equipment. So there's a nice synergy here where Norbliss is making software that we can use for our special imaging system, but they're also developing a software platform that's going to be useful for them in the future as a startup. Then the last scientific partner in the project is the University of Munster. And it's really important for us, as I've mentioned multiple times here, we're using OAM in scattering media, and we'd like to do our tests in a relevant test bed. We have a history of NKT and DTU working with Munster University on these special samples, the phantoms that they call them, where they use mouse retina, real mouse retina, and they're able to unfold and then preserve the retina in a resin. And that means we're able to have a real measurement sample to do these new measurements on quantum OCT. The last partner that's included in this project is RDTech. And they are a relatively new introduction to me in terms of EU projects, government-funded project frameworks. They are doing this socioeconomic analysis, and they have been digging at significant detail into how the project can help and also just affect the world in terms of economic output, but also social change and environmental effects of developing this new piece of equipment. And of course, they recognize that this is a very early stage research project. It's very difficult to make a commercial analysis of such a project at this stage, but I think they've done an excellent job looking across the fields and looking across the different hardware technology aspects that we're developing and coming up with an analysis. So that's everything that I have. You can see all of our partners there. We also have a website and we're on LinkedIn. So if you would like to join the website, please do. We have a newsletter that you can subscribe to, and the website is typically updated with the news from the project regularly. Thank you.
Thank you very much, Patrick, for introducing us to the optical coherence tomography and to this new equipment that you are developing with such an impressive team of partners. And I would like to invite the participants to write their questions in the Q&A, specially dedicated session, and we will be asking them and discussing them at the end of the second presentation. Now, I would like to welcome on stage our second speaker, and we will be shifting now from the eye dimension to the dimension of the Earth. So, the second speaker is Jean Lautier-Gaud, and he's a project manager at Time and Space Laboratory in Paris Observatory in France. And he will be presenting us a new European project that is just started about the gravimetry and the scanning of the Earth with this new equipment. Jean holds the PhD in quantum sensing and is from Sorbonne University and Paris Observatory, as well as MBA from Collège des Ingénieurs. For 8 years, he was a head of business development and sales at the startup Mach1s, and they created specialized quantum gravimeters. So it turned that Mach1s was successfully acquired and became Exail Quantum Systems, which is now commercially available product. Then Jean also co-founded another startup called Welling, which is pioneering the interconnection of quantum processors and creating quantum memories for the light. And now he serves as a project manager for the EQUIP-G project, which he will be presenting now, which is the European Quantum Infrastructure Project for gravimetry. We are very much looking forward for your presentation, Jean, and to learn more about how we will explore Earth with this new infrastructure.
Thank you for the kind introduction and welcome to everyone. I'm very glad to be here. So today, indeed, I will be presenting the EQUIP-G project. It's a Horizon Europe project that has just started. It stands for European Quantum Infrastructure Project for Gravimetry. And here the keywords will be, well, quantum for quantum technologies, of course, but infrastructure and gravimetry for Earth observation, because the project regards the monitoring of the subsurface due to natural or anthropic phenomena using terrestrial surface measurement with quantum sensors. In a nutshell, no need to be a specialist. Gravimetry is the measurement of gravity, which is the gravity pull exerted by the Earth on every mass, on every body. And this acceleration of the Earth's gravity is very powerful because thanks to the Newton law, we know that this is directly related to the mass distribution surrounded where you measure, which means that if you measure gravity, you have a direct information about the mass that lies underground. And especially if you measure gravity on points over a grid of points over a territory, then you can reconstruct the mass distribution underground, being cavities or reservoirs and so on and so forth. And if you keep measuring gravity over these stations, measurement stations, then you can follow how the underground evolves without digging with a very light infrastructure. And this is a very powerful method for resource management and risk assessment. For example, if your aquifer is being emptied because water is being pumped for agricultural purposes, you can follow this activity and monitor this activity with surface measurement of gravity. And in the same spirit, if you have a magma uprising within a volcano and the plumbing system of a volcano, you can keep track of the displacement of the magma and potentially one day predict volcanic eruptions. So it's a very powerful method. And here we are living a very exciting time because quantum technologies enable to provide a new generation of sensors called quantum gravimeters that show very interesting features, very good measurement performances that can outcome traditional technologies, but also very attractive operational features because these sensors are now transportable and quite easy to manipulate. And I want to highlight the fact that EQUIP-G is not an R&D project. It's really a matter of operation in the field. It's a matter of making technology available and democratizing the use of quantum sensors. And this is not sci-fi anymore. If you look at this picture, this is a picture taken last August in Greenland, where you see at the bottom a quantum gravimeter that has been deployed and has successfully measured in Greenland to monitor the mass balance of the ice sheet to monitor, help monitoring climate change. So our vision is that quantum gravimeters, oh, can't see the picture. Do you see the slides?
Yes, the slides are visible. I think you referred to the background of your slide, right?
Yes.
Mm-hmm.
Yes, exactly.
It's visible.
Okay, sorry about that. I was afraid that it was not displayed. So the vision of EQUIP-G is really to consider this new technology that is now mature enough to be deployed by non-specialists and consider that they can play a key role to monitor the subsoil for anthropic phenomena and also natural phenomena. And our mission is to design and establish a first network of gravity measurement stations and instruments to prepare a prototype of research, a future research infrastructure built around a shared park of quantum sensors that will be made available for a large community of users within Europe. And that's what I'm going to describe today. So in a nutshell, EquipG shows a large footprint. It stretches over 11 countries. We are here for 4 years, and the objectives are very well aligned with the Quantum Europe strategy to develop a network of quantum gravimeters for terrestrial measurement and build a shared park of instruments for a large community of users. Within EquipG, we will procure and test quantum gravimeters. We will deploy them in the field in various regions for use cases dealing with some of the most pressing societal challenges that we need to face in Europe. We will collect, store, and make available data, gravity data, for a large scientific community. And the goal is also to build up, to increase the community of stakeholders of gravimetry for Earth monitoring and monitoring of human activity. On the map, this is what's at stake, the various institutions that are within the project, and also a first description of the different activities that will stretch over the Europe for terrestrial, but also onboard measurement that I will comment on later. The consortium of EquipG is very powerful because it brings complementary experts for operation of quantum sensors, data management, for preparing the use cases. And we also have preliminary work for the infrastructure to evaluate this quantum gravimeter to make sure that the measurements are trustworthy for the community, especially over the years. The first topic within EquipG regards the procurement and the operation of instruments. So we will procure 7 quantum gravimeters, 2 graviometer sensors. So these are specific type of this technology to have enhanced measurement capability. And 1 version of an onboard quantum gravimeter will be developed and tested to fly on a fixed wing airplane and also in an airship. And within this work package regarding instruments, our work is to procure instruments, so work on the contract aspect, maintenance, terms and conditions. We need to receive them and test them to make sure that they are all measuring according to spec, and we have a thoughtful and complete understanding of their behavior. This will be done at the French National Meteorological Institute, LNI, and you see a picture of the facility of this infrastructure on the right, where here on this picture, various kinds of gravimeters are operated and evaluated on a site which is very well understood. When the gravimeters are properly inspected and validated, they will be sent in the field to address use cases, and people will be trained, so non-specialists, anyone interested in using such gravimeters will be trained to be able to borrow instruments and use them for their own use cases in their own regions. And I will come back on that because this is a very important aspect of the project. About the use cases, I wanted to show you how concrete it is and how embedded it is on our societal challenges. We selected 8 use cases, stretching from hydrology to try to better assess the charge and recharge of the water table. Gravimeter can also be applied to investigate how pollutant enters the soil, can help assess whether or not nuclear waste can be stored underground for long term. It is very useful for volcano monitoring, for climate change monitoring, and last but not least, to help spur the energy transition. It can play a key role for geothermal energy operations. And what you'll get from EquipG for the use cases is possibly in your region, in your territories, to propose new use cases and to request the use of such gravimeters for your own use cases. In terms of data, this was a clear objective for the consortium. We'll have a very significant number of sensors operating in the field for many years, and we want the data to be stored and made available for various future scientific investigation. And we will work under the FAIR principle. The data will be findable, accessible in open source, interoperable, and reusable for a wide range of users in the private sector and in the research sector. A key aspect for later will be to possibly have such data available within EPOS, the European Plate Observing System, which will be the very solid consolidation of this initiative. And for you, what's important to keep in mind is that you will be able to access gravity data in various countries for the use cases that I just described to exploit this data, and you will be able to learn how to leverage this data for your own monitoring activity in your own territories. The last part, but not the least, as I was saying, is to try to engage as most as possible with people interested in the monitoring of the subsurface, people already using gravimetry, but also people that are not very used to or might be afraid of gravimetry. We are really here to bridge the gaps and include any person, a policymaker, public agency, research lab that is involved in the monitoring of the subsurface. We want to include all of these mindsets to let them know that a new technology is available. It's not linked to a particular manufacturer, it's quantum gravimeters in general. And this technology can now be used on a broader scale. And actually within EquipG, we provide the sensors to the users so that these new potential operators are not obliged to buy a sensor from scratch to have hands-on first measurement campaigns, but can borrow from our consortium. And you can keep in mind that within this community building perimeter, we will organize 2 EU-wide workshops gathering the public and the private sector to raise awareness, but also present the results so that you can have a better idea of what's possible and hopefully spur new propositions for use in your territories. And to do that, EquipG will open 2 open calls so that external entities that are not part of the consortium can request the free use of quantum gravimeters. And within this program, operators will be trained. You will learn how to use it, and you will be able to receive the sensor and use it for your own use cases. Our mission is that at the end of the 4 years, so in 2029, we will establish a roadmap, a clear roadmap, and clear recommendations to the European Commission to establish a future European perennial entity that will manage this shared park of instruments and manage this network of gravity stations so that we have a consistent monitoring system of the underground for various use cases linked to our societal challenges. And in terms of the next steps, this is to give you some key dates, at least stretching over the next year, 2026. I want to really insist on 2 dates. The first EU-wide workshop that will take place next June in Germany. This is really open to a wider public. Everyone interested to follow this activity, propose new idea, learn what is possible. Really don't hesitate to join, sign in and participate. We will have technical talks, but also presentations from policymakers. So it's really larger audience workshop. And also the first open call to request the free use of quantum gravimeters that will be open in summer 2026, so that even if you're not part of the EquipG consortium, you can still benefit from this technology, you can be trained to use it, and you can apply for your own activity. In a nutshell, EquipG is a very ambitious and large Horizon Europe project. It stands for European Quantum Infrastructure Project for Gravimetry. And you can benefit it through 4 main avenues: to follow how quantum sensors can operate in the field for our own benefit, to learn how to use a quantum gravimeter and get a free loan of instruments. So we will train, we will provide assistance as a community. You will be able to get access to real field quantum gravimetry data. And basically, you will be part of a large community of users, of stakeholders, of monitoring the underground with quantum technologies, but also as a whole of people interested in monitoring the subsurface. I'll be happy to answer some of your questions. We have a brand new website, and you can also follow us on LinkedIn. So my name is Lautier-Gaud. I'm the project coordinator of EquipG, and I'll be happy to assist you with any questions. Thank you.
Thank you very much, John. This was impressive to hear about the ambitions of the project to provide a new eye, if you want, to visualize our planet and the surface of our planet, at least, and that it also aims to provide the access to it such openly and democratically. Thank you so much. We will now, I ask Patrick to come back to us as well, and we will now start our question and answer session. And I welcome again our participants to write their questions in this Q&A section that you see in the bar below. In this way, we can track best the questions and be sure we don't miss anything in the chat. And I see that we already have one question in the chat that is very moonshotting to my point of view, but I think we can transform it to something that we can answer. So the question was whether the work, I think it goes to to Patrick, will be somehow relevant for studying the DNA, the instrument that is provided. Where I think we could maybe envision that DNA is probably too small for the moment to be scanned. But if Patrick can wave us what are prospects for maybe increasing yet more the resolution of the instrument, and indeed maybe there are thoughts about the DNA that you have.
Yeah, absolutely. I think that's a great question in the right direction. I also agree with you, Oxana, the resolution required for imaging DNA is very high. So the resolution of a typical very high-end conventional OCT system is about 1 micrometer. If we would get double the resolution with quantum OCT, then we're talking about 500 nanometers. And this is actually on a very interesting scale that researchers have been pushing for with making higher-end OCT equipment, trying to be able to recognize or to resolve a cell. So in particular, you might think about being able to resolve the long retinal cells forget exactly what they're called, the long retinal cells that you have, which are the receptors in your eye. And this is something that I believe you will be able to resolve if you have 500 nanometers of resolution.
That's great. That's very interesting. Thanks a lot, Patrick, for reflecting on that. I also have some secret channel for the questions which came to us through the registration forms. And this one will be for Jean. And the question is, do we have any quantum sensors that help us to differentiate among different metals far beneath the Earth's surface?
So the answer is unfortunately no. I'd like that. We cannot discriminate between materials. It gives you information about density contrasts and mass changes. So this is why users of gravimetric data rely on other geophysical techniques and other geological data to spot any deposit of interest and to interpret the data. So this is a critical part of the workflow. However, it's not directly included in the EquipG perimeter. Our job is to provide working instruments and clean gravity data that are later handled by geologists and reservoir engineers, for example.
Mm-hmm. Yeah. Thank you very much. And yeah, I was suspecting this answer, but you never know.
Yes.
So the answer directly not, but with additional data that on the geological side, you can reconstruct things.
Yes.
Which
and
is
it's especially a good complement from seismic imaging, for example. So seismic imaging is a technology that is widely used in exploration, for example, for mineral exploitation or oil and gas industry. And gravimetry turns out to be a powerful technique to better interpret seismic imaging and possibly to lower the overhead of the seismic imaging. Something I forgot to mention is that gravimetry, it's appealing because it's surface measurement. So you basically, you come, you measure, and you go away. And it gives you, however, an information about what is inside at also very deep, so few kilometers depth. So it has a large penetration capability, if you may say, although nothing penetrates the ground. But you can have access to deep sources as well.
okay. That's very important data. Few kilometers.
Mm-hmm.
Mm-hmm. All right. One more question, which will bring us a little bit out of the scope of what we heard so far, but might be interesting to think as an application. And I think I can address it to both of you. So the curiosity was whether of the sensing that you are dealing with are capable to serve us in autonomous driving vehicles. So
I can start on that because this has been another dream of many persons, and for what regards quantum gravimeter or quantum accelerometers, or in more general quantum inertial sensors. It's a bit early if we envision, let's say, autonomous car or autonomous light drone. However, it's already used and can be used for autonomous large vehicles, such as large submarines. You can really consider gravity maps as a guidance system, because if you record very precisely and with a very nice spatial resolution the gravity field over an area, you can then navigate through this map by sensing real-time gravity without the aid of any GNSS external signal. What's to keep in mind is that these sensors, as you saw in the picture, they are transportable, but still remain bulky. So it's not for today nor tomorrow that we will have that on a regular car for, say, going to vacation, for example. So it's meant to stay in the area of large vehicles and critical operations so far.
Okay, so we could think about some vehicle which would go to explore a tunnel or a dangerous area, the tunnel that is to build or something of this direction.
Yes, and research actually now goes in the direction of quantum inertial platforms. So to really help a plane navigate autonomously, so measuring acceleration and rotations, so like traditional inertial navigation systems. But again, the quantum system remain bulky for the time being. So we are at the level of proof of concepts on the ground and first operation on board. So maybe in the later years, we'll have some first prototypes.
Okay, that's very good to know. Thanks, Jean. Patrick.
Yeah, I can make a comment on that. I think I would maybe the thing that comes to mind for me is something a little tangential from this, which is the hardware that's being developed for quantum technologies that is also useful for other technologies. And one thing that comes to mind is single photon detectors based generally on avalanche photon detection. And some of the projects that we've been involved in have been focused on hyperspectral imaging, for instance, using avalanche photon detection to increase the sensitivity of their imaging systems for long distance measurements with very few photons. So some of the technology that is being developed by this wave of quantum tech that's being driven at the moment is also very useful for other technologies outside of quantum, and potentially could be that the detection that must be so sensitive for detecting single photons also benefits few photon detection used for low light LiDAR imaging or distance LiDAR.
Great. Thank you so much, Patrick, for reflecting on that. Okay, now we've got one more question, and there is one more curiosity if there is the relation of the gravimetry network that Jean was talking about with the definition of the time frequency precision of the time to femtosecond precision, sorry, which is to outperform the current GPS. I would assume that this is related to other types of instruments, but I'm sure that Jean knows how to redirect us. You are mute, Jean.
Sorry about that. I'm not entirely sure I got the question, so I'll try to rephrase and answer, and you correct me if I get it off. So gravimeters measure the acceleration of the Earth's gravity to know the gravitational field around. And if we look at another type of quantum sensor, an optical clock, so it's a device that measures an optical frequency with the use of atoms. These devices are now so precise at 10 to the minus 18 in terms of resolution that the effect of gravity on the frequency count becomes big. And if we translate that in terms of usage for geodesy, so monitoring spatial references, optical clocks can now be used to sense the gravitational field. So before, the gravitational field was an effect, was a source of noise, you may say, on the signal of clocks, atomic clocks. But now optical clocks are so well controlled and so precise that it can be used to sense the gravitational field. And especially if you are able to compare remote optical clocks at nation scale or even continental scale, you are able to perform what we call height difference measurement. So it's still optical frequency that you measure, for example, at PTB in Germany and at NPL in the UK, or in Observatoire of Paris in Paris. But you measure frequency and you are able to retrieve an information about height difference, so which is very useful for geodesy. And this is something that is not possible with traditional GNSS technology. So here we have a new benefit that comes for free from this development of quantum sensors. And here the key aspect is this ability to compare optical clocks remotely on long distances through the availability of frequency transfer over optical fiber, for example, which is an initiative still ongoing in Europe that was started a decade ago. And now Europe has the chance to benefit from a network of optical fiber that can compare optical clocks in various cities.
Mm-hmm. You're talking about the Europe QCI, I imagine.
Not EuroQCI, it's more for a metrology purpose. So there used to be a project called CLONETS, funded by the European Commission. Now it turns to be Sensei as well for more sensing of the Earth through optical fibers. So it's basically the intimacy between various quantum sensors and the ability to gather them within a network to enhance new measurement possibility.
This is amazing. And now that we learned that the gravimetry can be measured also with the time measurement, with the optical clocks, practically, how would these two different measurement instruments like optical clocks and the gravimeters, how would the data from them combine, in a sense, compare? I imagine that they would allow to measure some different regimes or something
exactly. So
complementary.
Exactly, they are complementary. And just to be clear, they do not measure the same observable. They do not make the same measurement. But these are two complementary measurements that help to better understand gravity, the gravitational field on Earth. The optical clocks can help sense the gravitational potential, and gravimeters can help sense the acceleration of the Earth's gravity, which is the derivative of the potential.
Fantastic.
So that's the link. Data from gravimeters can be considered as the derivative of what can optical clocks provide as data.
Okay, so they can also be used as a reference for each other in a way.
Exactly. Especially what is very useful for the operation of optical clocks is to have gravimetry data to characterize the laboratory where optical clocks work, because you need to have a good understanding of the gravitational field evolution where your optical clocks lies to be sure that you understand what you measure with your optical clocks.
Okay. Yeah, right. So to clarify it all, the GPS has nothing to do with the gravimetry measurement for the moment.
Yes, exactly.
The optical clocks are very useful tools for GPS to work, because otherwise nobody would measure the time difference of signals. Although the gravitational measurements of those do not impact the GPS work directly.
Yeah, we can say that GPS is something different.
Yeah. Okay, then let me see what I have in my secret stock. Atomic liqueurs. Okay, I think we have gone through all, and we keep receiving the question in both now the chat and the Q&A, so I cannot ignore it. That we have a very proactive person who would like to contribute to the work of the project, and looking forward for the way how to apply for jobs and potentially work with you. And correct me if I'm wrong, but probably the new websites that you have of the projects are active, and you're posting there the work opportunities, I imagine, because with Epic G so ambitious and so many things to be done, I suppose you will need a lot of workers, new workers to be hired, and there should be a lot of job opportunities in this occasion. So actually that would be nice to hear how you plan to recruit in this area.
Yeah, indeed, there's a lot to be done. We are 20 partners, and each partner has its own hiring channels and hiring strategy. What I can offer, being the coordinator, is I can be the one-stop shop for job inquiries, and I'll be advertising for jobs within the consortium. I think that's the safest to make sure that a proper profile find a good fit regarding the capabilities and the skill set.
Great. Yeah. So I would also like to ask Patrick, because your project is coming to the end, right? And if you could reflect how many people you hired, how many human resources you needed to actually come to the doubling of the doubling, no, cutting half the precision of your instrument.
Yes, there would have been at least 20 people working on this project in the last 3 years. We've had a small rotation of some. I think the way to get into a project like this is to look for PhD postings or postdoc position postings. Usually the academic institutes, they're able to support a researcher for the jobs. As far as the private companies go, then NKT does, and I think all private companies have their own career websites. So that would be the place to look. And I think as far as remote goes, NKT is not a major, we work on hardware, so we don't have a lot of remote employees, but some who are doing more theory work could be looking for that kind of stuff.
Okay. Thank you so much, Patrick. Yeah. With this, I think we are done, and we actually already approached the end of the session. And I would like to thank a lot Jean and Patrick for being with us and for explaining us how we can apply quantum sensors under such different scales as from human eye to the planet Earth. This was a very impressive session, and looking forward for seeing you at the other occasions.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye.